All right, so now let's walk step by step to basically synthesize a few simple filters first, and then we'll see a couple more complex ones, essentially by having the coupling matrix. So there are essentially two different approaches we're going to see. One approach is, I would say, the easy one, the textbook approach, which basically allows you to synthesize your filter response by getting the G parameters. In fact, this is so simple that if that's the only thing that existed, it's unlikely the coupling matrix technique would have existed, because as we have already seen, once you have the G parameters, you basically have everything. But I still want to show you this so you can link the coupling matrix idea with the G parameters. Now, the second approach is a little bit more practically useful, and it actually comes from directly synthesizing the coupling matrix and therefore the topology and everything from the desired transfer function. So it's very possible that somebody gives you a transfer function that cannot be implemented with an approximation like a Chebyshev or a Butterworth one that actually has G parameters. So in other words, it's very likely that in real life you don't have G parameters. And so that means you have to go for the transfer function approach. So I'm going to basically show you a few different examples outlined here. And for these first examples, we're going to basically assume that we have totally lossless resonators, so infinite quality factor, and also synchronously tuned resonators, so you will see that basically all the self-coupling elements are basically equal to 0. So let's go for the first example. So let's say that we wanted to do a first order, so single resonator, Bessel-type filter with a 3 dB attenuation at omega is equal to 1. So synthesizing basically at the normalized domain, so that's why omega is equal to 1. Now, we have a first order filter, and that means that our coupling matrix will be 3 by 3. Remember, you have one row and one column for the source and the load. And so that means that always your coupling matrix will basically be n plus 2 times n plus 2, where n is the basically number of resonators. So you have now the coupling matrix shown here. So now let's discuss a couple of choices. So first of all the diagonal elements are 0 because we're talking about a synchronously tuned filter. There's going to be a coupling between the source and the first resonator and the only resonator. This is shown here as M01. And there's going to be a coupling between the first resonator and the load. This is basically shown as the M12. There is no coupling between the source and the load directly. And that's why you will see that the M02 is basically equal to 0. Right? So in other words, just by looking at this, you can basically see that the topology is a very simple one, is the one here. So this is the resonator and the load. And this is the coupling, the M01. This is the coupling, the M12. So you can see this as 0 node, first node, and second node. The first order Bessel response basically has the transfer function that you basically see right here. And as I said, we're going to basically see it from both points of view, both from the G parameters and from matching the transfer function. Now, in a transfer function case, you basically can calculate the Bessel transfer function, which I'm not going to basically do here. But if you go through the textbooks and you calculate the Bessel transfer function, you will find out that the transfer function is this one, the first order. Of course, you can do this for nth order, but I'm showing you here the first order so we can do the math quickly here together. This essentially has a single pole. The single pole is at -1, and of course, it's on the left-hand plane, as we discussed before, to basically ensure stability. So, second step, once I know my transfer function, is to calculate my S21 from the coupling matrix, and here it is. If you basically plug in all the matrices I showed you before, R, U, and M, and you use the equation I gave you before, you basically will get the S21 to be this number right here. Now, this number must be equal to the transfer function you're trying to implement, so we must make sure that this equation here is correct. And basically, that's it. The rest from here is to basically come up with the numbers. So, for example, here we have a symmetrical network. So the M01 will be equal to the M12. And so that means that 2 M01 squared should be equal to 1, which basically will give us the M01 to be plus or minus 1 by root 2. Now, it honestly doesn't matter whether you choose the plus or the minus. It's only a phase difference between the two, 180 degrees phase shift. And I'm going to use the plus sign here since, again, in this class, we're only concerned about amplitude responses and not phase. So indeed, if you go ahead and you plug in the calculated S21 and S11 based on the coupling matrix and with an M01 to be 1 by root 2, you will basically get this graph right here. And in this graph, I have also given you the group delay, which of course you can plot once you have the S21 and the S11. So let's see a second example so we can consolidate our learning a little bit. In this case, we're going to do a second order Butterworth-type filter. Basically, again, we're going to synthesize this in the frequency domain of omega is equal to 1. Since this is a second order filter, our coupling matrix will end up basically being 4 by 4. This is also a simple filter where we only have direct couplings. So you will see in the coupling matrix absolutely no cross couplings. In this case, we have the advantage of knowing both the G's, because it's a Butterworth filter, as well as the transfer function. So we can basically go and find the coupling matrix of this filter both ways. So let's first do the G parameters. So in the G parameters, I have given you in a previous lecture the equations for calculating them in a Butterworth case. So for a second order Butterworth case, these are the G parameters right here. And we have explicit expressions for finding the coupling values once the G parameters are known. So you can go back to your lecture notes and essentially recover the expressions I'm showing right here. And so clearly now we have a very simple coupling matrix from the G parameters. And as I mentioned before, this is a very straightforward way of calculating if you know the G parameters. And of course, this graph here shows essentially the validation of our calculation based on the expressions right here. Now, from the transfer function, it works exactly the same as we did before. I need to basically write down the transfer function for the second order Butterworth filter. I need to find the poles. The poles for a second order Butterworth are basically known, and they're shown right there. If you remember, those comes in conjugate pairs, but I will only choose the left-hand plane poles, which are the poles shown right here. And so I have the transfer function written explicitly in this box. In fact, this is a transfer function we've seen in a previous lecture as well. So once I have that, again, I can use MATLAB or any other symbolic calculator that you like. I can calculate the S21, shown here. I'll get rid of all the phase terms. For example, I don't really need this J. This simply shows that I have a 90 degrees phase shift. And I will basically take the magnitude of S21 and equate it with the desired H of S. So again, I'm just matching coefficients here, and here's the results for all the coupling matrix elements, which of course are the same ones as I calculated before. And basically that shows the second technique. There's a third example here, which I'm not going to do, but I have the solution here in the hope that you guys will actually work this yourself. So I have all the numbers. I really hope that you will do it and basically validate essentially what I have done here.